While modern factories spend millions on electricity and replace machines every decade, one workshop in rural England ran for 100 years without paying a single power bill. They used technology so simple that every engineer called it impossible. So why did it outlast everything that replaced it? Before we continue with the video, if you're listening right now, help me prove something wrong. My wife said I wouldn't even reach 1,000 subscribers, but I believe stories about old machines like this deserve to be heard. Help me show her that these videos matter. Please subscribe to our channel and let's keep these old machines' legacies alive. September 14th, 1854. The Cotswolds, England. Thomas Ashford stood beside the River Windrush watching his London-trained engineers shake their heads in disbelief. At 42, he was proposing something that defied every principle of modern industrial progress sweeping through Victorian Britain, while competitors rushed to install steam engines and prepare for the coming electrical revolution. Ashford was designing a workshop powered entirely by river current. No coal deliveries, no fuel costs, no dependency on the industrial supply chains that were making fortunes for steam equipment manufacturers across England. The engineering assessment from his London consultants read like a death certificate. Water power is antiquated technology suitable only for grain mills. Modern precision manufacturing requires the consistent power output that only steam engines can provide. Seasonal water flow variations make reliable production scheduling impossible. But Ashford saw what the steam engine salesman deliberately ignored. Every workshop in Birmingham and Manchester paid coal suppliers whose prices fluctuated with mining strikes and transportation disruptions. Every factory faced complete shutdown when boiler maintenance required days of costly downtime. Every manufacturer accepted fuel expenses as unchangeable operational costs. Through the morning mist rising off the Windrush, Ashford surveyed the abandoned flour mill he'd purchased for 8/47. The existing water wheel was primitive, but the river's flow rate remained remarkably consistent year-round. Spring snowmelt from the Cotswold Hills provided increased volume during summer months. Autumn rains sustained flow through winter. Only severe drought affected output, and historical records showed the Windrush had maintained reliable flow for over 300 years. His chief engineer, Robert Blackwood, had spent 6 weeks measuring water velocity, calculating volumetric flow rates, and designing a mechanical power transmission system that seemed impossible to steam-trained machinists. Multiple water wheels driving separate workshops through an integrated shaft and belt system that could distribute power exactly where production demanded. The mathematics were undeniable. Steam engines converted roughly 6% of coal's energy into mechanical work. Water wheels achieved 65%. Efficiency converting gravitational potential energy into rotational force. No fuel costs, no boiler maintenance, no dependency on coal mine labor disputes that could halt operations without warning. London investors rejected Ashford's funding proposals with condescending explanations about progress and modernity. Steam power represented the future. Water power was medieval technology that serious manufacturers had abandoned for good reason. But Ashford had inherited $12,000 from his father's textile business, enough to build his vision without external capital or quarterly profit expectations. Construction began in October 1854, and the first water wheel turned on March 3, 1855. What Ashford couldn't have known was that his water-powered workshop would outlast every steam-powered competitor in the Cotswolds by more than half a century. The question wasn't whether water power could work. The question was whether British manufacturing would recognize its advantages before the entire industry collapsed into dependency on power sources they couldn't control. The engineering challenge wasn't generating power, it was distributing it precisely where manufacturing processes demanded. Ashford and Blackwood designed what they called the cascade system, a mechanical marvel that would become the workshop's defining advantage. 3 separate water wheels, each 18 feet in diameter, operated in series along a 200-foot stretch of the Windrush. The primary wheel drove heavy machinery requiring maximum torque, metal lathes, grinding wheels, and sawing equipment. The secondary wheel powered precision tools needing controlled speeds, drills, polishing stations, and milling machines. The tertiary wheel operated auxiliary equipment including ventilation fans and material lifts. Unlike steam engines that provided single-speed output requiring complex gearing systems, each water wheel could be independently regulated through sluice gates controlling water flow. When production demanded increased lathe output, operators opened the primary wheel's gates. When precision drilling required reduced speeds, they partially closed the secondary wheel's flow. The mechanical transmission system proved even more innovative. A main drive shaft ran the length of the 300-foot workshop, powered by all three water wheels through a differential gear arrangement Blackwood had adapted from mill machinery. Individual workstations connected to this main shaft through leather belt drives that could be engaged or disengaged as production schedules required. This created operational flexibility that steam-powered competitors couldn't match. A Birmingham workshop using steam power ran all machinery simultaneously at whatever speed the steam engine provided. Ashford's cascade system allowed selective operation, running only the equipment current orders required while conserving power for other stations. The workshop's specialty became precision brass fittings for steam engines, a delicious irony that Ashford noted in his personal journals. While competitors used steam power to manufacture steam components, his water-powered operation produced superior fittings at 30% lower cost because he paid nothing for fuel. Quality control advantages emerged immediately. Steam engines vibrated constantly, affecting precision work on sensitive equipment. Water wheels produced smooth rotational force without the harmonic vibrations that plagued steam-powered machinery. Brass fittings requiring tolerances within 1/1000th of an inch could be manufactured consistently because the cutting tools operated without the subtle shaking that steam power introduced. The workshop's first major contract came from the Great Western Railway in 1857 for 10,000 brass valve fittings. Competitors bid based on steam engine operating costs plus coal expenses. Ashford bid based solely on labor and materials, undercutting every competitor by 25% while maintaining profit margins that would have been impossible with fuel costs. Orders accelerated as railways, factories, and municipal waterworks discovered that Ashford's fittings outlasted competitors' products because they'd been manufactured with superior precision. By 1860, the workshop employed 47 craftsmen operating in shifts that maximized daylight hours while the water wheels ran continuously. The cascade system had proven that mechanical engineering could overcome dependency on fuel suppliers, creating competitive advantages through systematic design rather than accepting operational costs as unchangeable business conditions. By 1875, something unexpected had happened at Ashford's workshop: the development of generational expertise that steam-powered competitors couldn't replicate through equipment purchases or worker training programs. Master craftsman William Henshaw had worked at the workshop since 1858, initially as a 14-year-old apprentice. After 17 years of continuous operation, he could diagnose water wheel performance issues by listening to subtle changes in the mechanical rhythm. A slight increase in bearing friction produced harmonic frequencies that Henshaw detected before damage occurred. Seasonal variations in water temperature affected metal expansion rates, and experienced operators adjusted belt tensions accordingly. This institutional knowledge created quality advantages that newer workshops couldn't duplicate. When a complex order required brass fittings with internal threading that standard equipment couldn't produce, Henshaw designed custom tooling that utilized the water wheel's variable speed capabilities. By adjusting sluice gates to provide precise rotational velocities, he could cut threads that steam-powered operations achieved only through expensive specialized machinery. The workshop's apprenticeship system formalized knowledge transfer across generations. Young craftsmen spent 7 years learning not just metalworking techniques, but water wheel management, mechanical maintenance, and the seasonal rhythms that affected production schedules. This created workforce stability that steam-powered factories never achieved. Steam engine operations suffered constant worker turnover because the technology remained relatively standardized. A machinist trained in Birmingham could work in Manchester without significant adjustment period. But Ashford's cascade system required specialized understanding of how water flow rates affected power distribution, making his trained workers essentially irreplaceable. This became a strategic advantage during labor disputes that paralyzed British manufacturing throughout the 1870s and 1880s. When coal miners struck for better wages, steam-powered workshops faced complete shutdown because they couldn't operate without fuel. Ashford's operation continued uninterrupted, capturing market share from competitors who couldn't fulfill orders during strikes. The workshop's production records from 1880 reveal the compounding advantages of institutional knowledge. Average production time for complex brass fittings had decreased by 40% compared to 1860 levels, despite using identical equipment. The improvement came entirely from operator expertise, craftsmen who understood precisely how to adjust water flow, belt tension, and cutting speeds for optimal efficiency. Financial independence from fuel suppliers created psychological advantages that manifested in worker loyalty and community stability. Employees understood that their jobs didn't depend on coal mine operations or steam equipment manufacturers. The river Windrush would keep flowing regardless of industrial disputes, political upheavals, or economic recessions. By 1885, the workshop had operated for 30 years without a single year of financial loss. This stability allowed Ashford to pay wages 15% above regional averages while maintaining profit margins that steam-powered competitors couldn't match, despite paying lower wages and accepting thinner margins. The Cascade system had created not just a manufacturing operation, but a self-sustaining industrial ecosystem that accumulated competitive advantages through continuous operation rather than equipment replacement or technological upgrades. The 1890s marked the workshop's golden age, as Ashford's son Edward introduced innovations that proved water power hadn't reached its engineering limits. It had merely been abandoned prematurely by industries chasing electrical modernity. Edward Ashford's 1892 installation of an overhead cam system revolutionized the workshop's precision capabilities. By mounting adjustable cams on the main drive shaft, individual workstations could receive programmed motion sequences that automated complex manufacturing steps. A single water wheel rotation could trigger multiple tool movements in precise sequence, positioning, drilling, chamfering, and withdrawing, without human intervention. This mechanical automation achieved results that early electrical motors couldn't match. Electric power required expensive switchgear and control systems. The cam-driven water power system used purely mechanical timing, eliminating electrical components that failed regularly in the humid workshop environment. The workshop's expansion to 73 employees in 1895 demonstrated how patient capital created compounding returns. Unlike steam-powered competitors who faced equipment replacement every 15-20 years as boilers corroded and pressure vessels weakened, the water wheels required only bearing maintenance and occasional wooden paddle replacement. Operating costs remained nearly fixed, while production capacity increased through incremental improvements. Edward's most significant innovation came in 1898 with the installation of a fourth water wheel dedicated exclusively to electrical generation. This hybrid approach captured both technology's advantages, reliable mechanical power for manufacturing, with limited electrical power for lighting and small tools requiring portability. The hybrid system cost $340 to install compared to over $2,000 for the steam engine plus generator systems that competitors were purchasing. More importantly, it maintained the workshop's fuel independence. The water wheel generated electricity during operating hours without consuming coal or requiring separate boiler operation. Quality improvements from water power became quantifiable as precision measurement technology advanced. 1900-era micrometers could detect dimensional variations that earlier gauges missed, and testing revealed that Ashford's brass fittings maintained tolerances 30% tighter than steam-manufactured equivalents. The difference traced directly to vibration-free operation that water power provided. Major contracts followed. The Royal Navy ordered 50,000 brass fittings for warship construction in 1902. The London Underground specified Ashford fittings for tube line expansion in 1905. Municipal water departments across England preferred Ashford components because decades of proven reliability demonstrated superior metallurgical quality. Peak employment of 89 workers in 1908 created economies of scale that smaller workshops couldn't achieve. Administrative costs and facility maintenance expenses spread across large production volumes reduced per-unit overhead to levels that made the workshop profitable even during economic downturns that bankrupted competitors. The workshop's 50th anniversary in 1905 passed with minimal celebration, but internal records revealed extraordinary achievement. 5 decades of continuous operation, 0 years of financial loss, 3 generations of Ashford family management, and manufacturing quality that had become the British standard for precision brass components. Edward Ashford's innovations proved that water power wasn't obsolete technology. It was fundamentally superior for applications where fuel independence and mechanical reliability mattered more than the convenience of on-demand electrical switching. The 1910s brought the challenge that should have destroyed Ashford's workshop. Electrical power was transforming British manufacturing with conveniences that water power seemingly couldn't match. Electric motors could be installed anywhere, required no complex mechanical transmission systems, and provided instant on-demand power through simple switches. Competitors who'd survived the steam era now rushed to electrification, spending thousands of pounds on motor installations and electrical infrastructure. Industry publications declared water power definitively obsolete, suitable only for rural operations too backwards to modernize. But Ashford's workshop demonstrated that operational economics mattered more than technological fashion. While competitors paid monthly electrical bills that consumed 8 to 12% of gross revenue, the workshop's only power cost remained minor water wheel maintenance. A 1915 internal analysis calculated that fuel independence provided cost advantages equivalent to 15% higher profit margins compared to electrified competitors. The First World War proved water power's strategic value. German U-boat campaigns disrupted coal shipments, causing electrical brownouts that shut down factories across Britain for days at a time. Munitions production demands overwhelmed electrical grid capacity, forcing manufacturers to operate on rationed power schedules. Ashford's workshop ran continuously throughout the war, limited only by material availability rather than power constraints. The War Office contracted for 200,000 brass shell casings, specifying Ashford's operation specifically because water power guaranteed uninterrupted production regardless of coal shortages or electrical rationing. Wartime production pushed the cascade system to maximum capacity. All 4 water wheels operated 20 hours daily, with only nighttime darkness forcing shutdown of workstations requiring precise visual inspection. The workshop employed 127 workers in 3 shifts, producing brass components that quite literally kept British artillery operational. Post-war recession eliminated competitors who'd borrowed heavily for electrical modernization. When demand collapsed in 1921, workshops carrying equipment loans faced bankruptcy while servicing debt on idle machinery. Ashford's operation survived by reducing shifts and operating only equipment that current orders required, a flexibility that debt-burdened electrified competitors couldn't match. The 1920s brought unexpected validation when electrical reliability issues plagued British manufacturing. Early electrical motors failed frequently, requiring expensive replacement and causing production delays. The workshop's 70-year-old water wheels continued operating with nothing more than bearing lubrication and occasional wooden paddle replacement. Industrial engineers from Birmingham visited in 1927 to study the cascade system, recognizing belatedly that water power's supposed disadvantages were actually strategic strengths. Fuel independence, mechanical simplicity, and minimal maintenance requirements created operational resilience that electrical complexity undermined. By 1930, the workshop had outlasted every steam-powered competitor that had mocked Ashford's 1854 vision. It had survived the electrical revolution that industry experts insisted would make water power extinct. 75 years of continuous operation proved that engineering fundamentals, energy efficiency, fuel independence, mechanical reliability mattered more than the technological fashions that drove competitors toward dependency on power sources beyond their control. The question facing British manufacturing wasn't whether water power could compete with electricity. The question was whether anyone understood the true competitive advantage came from controlling every operational variable rather than accepting dependency as the price of modernity. The 1940s brought challenges that water power's advantages couldn't overcome, not through operational failures, but through fundamental shifts in manufacturing, economics, and national industrial policy. World War II pushed the workshop to its absolute limits. Government contracts demanded production volumes that required round-the-clock operations, but the Windrush's flow couldn't power all workstations simultaneously during low-water summer months. For the first time in 85 years, the workshop installed supplemental diesel generators to maintain wartime production quotas. This dependency, though temporary, revealed a strategic vulnerability that peacetime manufacturing would exploit. Competitors using full electrical power could install equipment anywhere, scale operations instantly through additional motors, and operate independent of geographic constraints. Ashford's workshop remained tied to the Windrush's flow rate, a limitation that had been an advantage for decades but now became a ceiling on growth potential. Post-war industrial policy accelerated the shift. Britain's nationalized electrical grid provided subsidized power to manufacturing operations deemed essential for economic recovery. Competitors received electricity at rates below actual generation costs, creating artificial price advantages that made fuel independence economically irrelevant. Employment began its inevitable decline. The 127 wartime workers dropped to 84 by 1950, then to 62 by 1955. The reduction wasn't due to decreased demand, but to automation that reduced labor requirements across all manufacturing. Electrical operations could install automated equipment from any supplier. Water-powered equipment required custom mechanical engineering that few craftsmen still understood. The workshop's specialized brass fittings maintained quality advantages, but mass production techniques made price competition increasingly brutal. Competitors using automated electrical equipment could produce acceptable quality fittings at 40%, lower costs through economies of scale that water power's geographic constraints prevented matching. Robert Ashford, Thomas's grandson, faced decisions his predecessors never confronted. Modernization required abandoning the cascade system for full electrification, eliminating the fuel independence that had sustained the business for a century. Maintaining water power meant accepting declining market share as customers prioritized lowest-cost suppliers over superior quality. The 1960s brought final recognition that manufacturing economics had fundamentally changed. Just-in-time delivery expectations required production flexibility that water flow variations couldn't guarantee. International competition from workshops with lower labor costs made British manufacturing unprofitable regardless of power sources. Government regulations mandating electrical safety standards imposed compliance costs that small water-powered operations couldn't absorb. Employment dropped to 34 workers by 1965, then to 19 by 1970. These weren't layoffs, but natural attrition as retired craftsmen weren't replaced. The institutional knowledge that had created competitive advantages for generations now had no economic value in markets that prioritized cost over quality, convenience over reliability, quarterly profits over generational sustainability. The final contracts came from specialty applications where superior quality justified premium pricing: scientific instruments, marine equipment, aerospace components. But these represented boutique markets insufficient to sustain operations that had once employed over 100 workers, producing hundreds of thousands of components annually. March 15, 1955. Exactly 100 years after the first water wheel began turning, Robert Ashford made the decision that would end continuous water-powered operations. The workshop would cease manufacturing and transition to what he called demonstration operations, maintaining the cascade system as a working museum, while the family sold the surrounding land for residential development. The economics were irrefutable. The property's real estate value exceeded the workshop's annual revenue by factors of 10. Continuing operations meant refusing $250,000 from developers for land worth perhaps $15,000 as an industrial site. Patient capital had its limits, and 3 generations of Ashford family management recognized when history had rendered their engineering achievement economically obsolete. But Robert made one decision that preserved the cascade system's legacy. Rather than scrapping equipment for metal value, he donated the entire workshop to the National Trust, with an endowment providing perpetual maintenance funding. The water wheels would continue turning, the machinery would remain operational, and future generations could witness mechanical engineering that modern manufacturers had completely forgotten. Today, the workshop operates as a living museum with the water wheels powering demonstrations twice daily for visitors who arrive expecting quaint historical curiosities and leave understanding that their ancestors had solved engineering problems that contemporary manufacturing hasn't rediscovered. The operational advantages that sustained Ashford's workshop for a century remain mathematically demonstrable. Zero fuel costs, minimal maintenance requirements, mechanical simplicity that eliminated dependency on external suppliers or utility companies. Modern CNC machines require software updates, electrical infrastructure, and planned replacement every 10-15 years. The workshop's water wheels have operated for 170 years, with nothing more than bearing maintenance and occasional paddle replacement. The institutional knowledge that created generational competitive advantages has partially survived through the Trust's apprenticeship programs. Master craftsmen now in their 80s train younger engineers in water wheel management, mechanical power transmission, and the seasonal rhythms that affected operations for a century. This knowledge represents manufacturing wisdom that no university engineering program teaches because modern industry dismissed it as obsolete. The numbers validate everything Thomas Ashford envisioned in 1854. His workshop operated continuously for 100 years, survived 2 world wars, outlasted every steam and electrical competitor in the region, and maintained profitability through recessions that bankrupted manufacturers who'd modernized according to prevailing industrial wisdom. The 3 water wheels still turn on the river Windrush, their 18-foot diameters rotating with the same smooth mechanical precision that powered British manufacturing excellence for a century. They represent not nostalgia for simpler times, but proof that engineering fundamentals, energy efficiency, fuel independence, mechanical reliability, create sustainable advantages that technological fashion and quarterly profit optimization consistently sacrifice. The deepest question isn't why Ashford's water-powered workshop survived 100 years. The question is, what other proven engineering principles has modern manufacturing abandoned in pursuit of convenience? And what would industrial resilience look like if we remembered that true competitive advantage comes from controlling operational variables rather than accepting dependency on systems we cannot control?